to the sections of configurations and variability. I'm the section chair for the sections. My name is Xinhui Tan. I'm an assistant professor in Southern University of Science and Technology in Shenzhen, China. So this time we have all papers in the sections are either technical paper or journal first papers. So there will be each of the talk will be around 20 minutes. So the first speaker today, he's actually going to represent his colleagues because his colleagues couldn't come due to the visa issues. So the talk that he will present is ACT GAN, automatic configuration tunings for software systems with generative adversarial networks. Let's welcome the speaker, Alibaba.
Okay. Hi everybody, just 1 minute to open the presentation.
Okay.
Hi everybody, today I would like to present ACT GAN paper, automatic configuration tuning for software system with generative adversarial networks. First of all, I'm not the author of this paper, so there may be questions that I will not be able to answer. So I will give the author email at the end, so you could email him. Oh, I'm sorry. Should I start from the beginning or continue? Okay. So our agenda for today is the quick background and the related work, overview, and then summary and experiment. So for giving system under tune, we call the SUT, where there are workload W and time constraint TC, we try to find configuration C that maximize the performance B. So configuration have a significant impact on performance because of that software system are complex with many configuration options that control almost all aspects of their runtime behavior. So with this complexity, tuning a large number of configuration parameters required a deep understanding of the target system and usually surpass the ability of typical user. So with this complexity, tuning a large number of configuration parameters require deep understanding, as we said. So as a result, users often have to accept the default setting. Some organization hire a human expert to configure their software system. So our goal here is to find the optimized parameter that can obtain better performance. So many existing approach focus on exploring and learning good performance estimation model. The accuracy of such model often suffer when the number of available sample is small or when it's under given tuning time constraint. So however, the main challenge here are heterogeneity. Software systems that require configuration tuning are highly diverse in terms of workload, performance metrics such as, for example, throughput, execution time, and transaction per minute, for example. Second challenge is complexity. Given different performance metric and different workload, software system can have highly complex performance surface. So third challenge here is overhead. It's often costly to evaluate the performance of individual configuration in a large software system because no performance simulator exists for general systems. So software systems often provide a large number of parameters so that user can configure them for their specific scenario. However, for configuration tuning require a deep understanding of the software system, which beyond the ability of a regular user. So here are a category of different approach to choose different parameter. Sorry. So for example, most related one is learning based. So the pros and cons. For example, the pros here, utilization of prior knowledge of the system, and the cons is that it needs a lot of samples. So let's go through overview and design. So our hypothesis that good configuration often share certain hidden structure. Therefore, instead of trying to improve the performance estimation of a given configuration, we focus on capturing the hidden structure of good configuration and utilizing this learned structure to generate better configuration. So for a given system under Tune, let's take, for example, MySQL as a software system. We are, our load is W. We have actually constraint time here that limit our experiment. And we try to find the configuration C that maximize the performance P in given execution time. So we propose ACTGAN to achieve this goal. We have implemented and evaluated ACTGAN using 17 different workloads with 8 different software systems. The results show that ACTGAN outperformed the default configurations by 76% on average, and 6 state-of-the-art configuration tuning algorithm by from 6 to 64%. So here, you could see the difference between the prediction-based model and the generative-based model. So our goal is not just classifying or clustering. We are trying to generate a sample or parameter that behave similar to the good ones. So we know that we have good parameter and we have like regular one. So we try to generate parameter that behave as good as the good one that we already know. So here, so our hypothesis that good configuration often share certain hidden structure, as we mentioned. It's possible to capturing such hidden structure. So we give an example here how that certain metric. Sometimes you need to decrease the certain metric, and sometimes you need to decrease it. So all these behavior you could generate a new parameter that behave as good as the good one that you already know before. So this is called about the random sampling. That is, it's simple, and most importantly, it can effectively share for a large configuration space, especially when configuration parameters are not equally important. So the idea behind GAN, because we use GAN here. So the idea behind it's pretty simple, but it's also very beautiful. So in a sense, what we have is two neural network. We have the generator and we have the discriminator. So let me see here. Okay. So the generator is in charge of doing the following. It gets a randomly sampled noise vector as an input. In most cases, we will sample from Gaussian distribution. We take that noise vector and we input it into the neural network. So we follow through a hidden layer, and at the end we have a generated sample. So this generated sample is then fed to a second neural network, the discriminator. So, and the discriminator has one job. It needs to look at the sample and decide whether the sample comes from the actual data set, the good one, the real configuration, or the one that we know that work well with that training on, or whether that sample configuration come from the generator that we had. So, and because we controlling the training process, we have the label. So we know for each configuration that we fed to the discriminator whether that configuration was a real one coming from the dataset or a generated configuration coming from the generator. So, and by using the label, we can basically backpropagate a training loss through this discriminator network in order to make it better. So the most important trick in this pipeline is to make sure that both these networks are well balanced during the training, so that no one of them get upper hand. And if you manage to do so and you train it for long enough, then eventually that what you will have is a generator that have been training for the feedback of this discriminator network, and can manage to generate configuration that look like very similar to the data set that we have training on. So, did I pass one? Yes. So this is the parameter that we use in our training. So as you see, we use Adam optimizer with momentum 0.5, this learner grade, and how many epoch they have, and the batch size. So we tried different numbers, and this was the best result that we get out. So at the beginning, we estimate the number of samples. So we used random sampling to generate initial samples. Then we train both generator and discriminator using the best configuration. At the end, we use the generator to recommend number of configuration and return the best one. Sorry. Okay. So for experiment settings, we run the experiment on 8 different software systems. Each system has different performance metric and different number of tuned parameter. So as you may see here in the 4th column, you find first number like the tuned parameter, and last number is the number of parameter. So what happened here, we asked expert to choose which critical parameter that really affect the performance, and we only tuned that numbers, because then as you see the number of parameters is very, very huge. So we only get 11, for example, for the Kafka, 11 out of 169. We run the experiment again with 6 basic baseline algorithm, and ActGAN outperformed all of them. So here is some results. This graph shows the experiment of Kafka software with different workload on x-axis. Y-axis show the improvement in performance, and we used random sample as baseline 0. Each bar represents different algorithm. Yellow bar are ActGAN. As you see, ActGAN outperformed the other algorithms. So here's another software system called Spark with different workload. ActGAN again outperformed the other algorithms. So here's a summary of 6 software systems on the x-axis. And again, ActGAN outperformed the other algorithms. Sorry. Okay. So the summary that, we propose ActGAN, a novel approach to address CTSS problem from unconventional direction. So our hypothesis was that good configuration shared certain hidden structures. So we developed ActGAN algorithm. We use random sampling to generate a small number of initial sample in a high dimensional parameter space. They directly learn and utilize the hidden structure of existing well-known good configuration using generative adversarial network GAN without need to of learning performance prediction model. So the experiment results show that ActGAN outperformed default configuration by 76% on average, and 6 state-of-the-art tuning algorithm from 9 till 53%. Thank you. And I'll put the email for the author, so you could email him if I couldn't answer. But okay, if you have any question, please ask.
Thanks for the presentation.
Okay.
So, it might sound a bit aggressive as a question, I don't mean it.
Okay.
What is the motivation behind doing ActGAN? Meaning,
Yeah.
there should be a problem that the other algorithms do not really they couldn't address, right? In order for the authors to
Yeah.
go and suggest something like seemingly complicated as putting all this architecture together. So I know you have this line about challenges,
Yeah.
but they sound a bit generic to me. So I've used, for example, Bayesian optimization in order to do the tuning at runtime. So and I know that Bayesian optimization builds a performance model as it goes, etc., etc. You can also learn essentially which parameters are interesting to use and which are not. So do you have an answer to as to which specifically was the challenge, the problem that they want to address?
So do you mean the other algorithm was the issue with them that didn't
Yes,
let
what
them
was exactly-
outperform
yes,
the one?
What was the issue with other algorithms? Yeah.
Yeah. So I cannot answer this question like directly, but in general, like what happened here that we find that the ActGAN outperform the others. So the reason that what's going on here that we're using GAN, you are taking generating a sample from same distribution from well-known parameter that you already know. So what happens that at the beginning you collect very good performance, and from those you're trying to generate new ones that are good from the same distribution. So what happened here that you don't just start from nothing. So you already have like very good ones, and you try to generate new one that behave the same good as the good one. That from the other algorithm they have different yeah.
For convergence, right?
Yeah.
So you convert faster.
So
in that case, right?
yeah, some of them they start from scratch, from just random. Some of them they learn from the experience. So everyone have different technique to reach the goal. But here you see the idea, the basic idea that okay, we know some good things. Let's try to make like them.
Yeah, I get it.
Yeah. So the goal is that there's hidden structure in good configuration. Let's try to use this one to make a new good ones.
Any other questions?
Any other question?
So, yes.
So my question is, I think you focus on use samples on some configuration, but you also need to train. As I remember, it's 150,000 apples. So I want to know the training time. I think this time should be also add to the performance tuning time. So do this approach really outperform the others? I think the training and the sample, the number of samples, I should also want to compare it. You have it.
Yes. So what happened? We have 316 good examples, and we use them. And all the algorithm that we try, they have the same limitation. For example, they have the same time limitation, and they have the same sample, so everything are the same. Whatever you feed it, we feed everything to make it feel comparison between them.
Okay, so all the methods use the same sample, number of samples.
Yeah. And the main thing here that you have time constraint, which make like challenge for other algorithm to beat this one, because you have certain time you have to finish in.
Other questions? Let's go for
Okay.